Good catch, James. Good catch. No, I mean, in the sense that like assignment 12, it doesn't require anything from this week, right? Like you have all the tools to do it. It's just we didn't use the word critical point. So that's literally sort of like the only difference, right? Assignment 12 says, find the points where the gradient of this thing is equal to 0. And that is the definition of a critical point. So in that sense, again, we have to find the critical points of a function, but we did something similar to that even last week when we first learned about gradients. So there isn't anything there that requires this week's material. Oh, yeah, I thought it was pretty nice. We scaffolded a lot, so no part should be too bad. So Brian, can you say like which maybe subpart for you thought was a mess? Okay. It's a pretty cool thing. If any get a chance to study PDEs, they're a really interesting sort of field of subject. And there are actually, it is a big research field mathematically, but that being said, it's pretty complicated. This is a very technical field. PDE is super important though, right? They show up everywhere. So being able to know how to handle a PDE is a nice thing, but probably for most of you, it's not too big a deal, but it is a cool thing to study. There's a lot of like Fourier analysis in there, which I think is super cool. If you've never had a chance to even see Fourier analysis, it's like you break functions that aren't like into their harmonics. So there's a lot of application there to things like music or signal analysis, encryption, compression, lots of cool stuff in there. And then that shows up when you do things like PDEs, especially the wave equation. Okay, I'm going to lock this down in 30 seconds. This is the sort of thing that just like, if you know what the question is asking, in theory, you don't even have to solve it, right? You could just plug all these points in and see, which, if any of them actually give you an answer. All right, let's take a look. Class is leaning towards A. A is absolutely the correct answer. So the 0.14 is a critical point. You can see that 0, 0 is actually not going to work. When you take the y derivative of this function, you're going to get a -7 show up, right? So that's not going to work out. But let's try this. Let's see what we get. So remember, we're looking for critical points, right? Because we're looking for critical points, we want to figure out for what points is the gradient equal to 0. Right? So we've got this function here, f of xy is 2x squared plus y squared minus xy minus 7y. And a critical point is any point which satisfies this, right? 0, 0. So just like, again, when we first learned about gradients last Tuesday, we had a question like this, and generally we said this could be a nonlinear system of equations that we might need to solve. So let's compute the gradient, right? Which remember is just the vector of partial derivatives. So we're going to take the x partial derivative. So that gives us 4x minus y. Then we take the y partial. That's going to be 2y minus 7 like that. we're going to set that equal to 0. Now, this is going to give us two equations. Now, in this case, it actually gives us two, this is actually a linear system. Right, so we get 4x minus y equals 0. And 2y is equal to 7. Did I make, oh, I missed an x, sorry. Someone's got to yell at me. So 2y minus x minus 7, right? So negative x plus 2y equals 7 like that. See, I just had to look up. There were people yelling at me that I'd missed the x, but. Okay, and again, so if you get it to this point, all you have to do is actually plug the numbers in, or alternatively, you know how to solve a linear system, right? So you can do this one the high school way. It's two equations and two variables, or two equations and two unknowns. But alternatively, you can write it as a matrix and you could row reduce that matrix. But this gives you x is equal to 1 and y is equal to 4, right? And you can see 0, 0 is actually not a solution precisely because this 7 here sort of screws all that up. Okay, so that gives us x is equal to, or sorry, xy is equal to 1, 4, and that's our critical point. Okay, why did I write equal to 0, 0? So this is the definition of a critical point, right? So remember, right, when we were doing single variable calculus, the definition of a critical point is that where the derivative is equal to 0. The multivariate definition of a derivative is this gradient thingy, right? It's like this thing. And the multivariable version of 0, 0 is this thing. What I mean 0, 0 is not a solution? I mean 0, 0 is not a solution to this, right? If you plug 0, 0 into that, you don't get, like, if you do this, you don't get 0 on the right-hand side, right? So it's not a solution. How did I get x equals 1? I mean, you have to solve it, right? Like, I didn't solve it, but we know how to solve these sorts of things. So you actually have to go, you go through and you actually solve it, but, you could do something like what? Add twice the first equation to the second equation. That gives you, 7x is equal to 7. That gives you x is equal to 1. So you could do something like that or put it into a matrix, right? For -1, -1, 2, 0, 7, and row reduce to that. I mean, like, you could, I could get the answer if I'd like solved it in my head, but no, like, yeah, I just, I get it to a point where you can plug it into Octave or something and you can solve it. What is the significance of 0, 0? Because it was an option, right? Like, a bunch of students said 0, 0. And so I'm pointing out that 0, 0 is not a solution just because it was an option that a fair number of students picked. And I think it's probably tempting to like see a polynomial and suppose that 0, 0 is a solution. Exactly. Yeah. You get 0 is equal to 7. And that's why, that's why it's not a solution. So I'm just bringing it up just to point out, like, you can throw those answers away right away because you can see that 0, 0 actually doesn't solve this. And same sort of thing. This is what I'm saying. Like, once you get to this point, right, and you get this system of equations, in this case, it's multiple choice. You could just plug those numbers in, right? You don't even have to solve it. But again, we all know how to solve this. So you could imagine maybe there's even a situation where we give you some big ugly function, right? 5 variable function. And in order to solve it, you have to solve a system of 5 equations, right? And how would you do that? Well, you would use linear algebra to do that, right? You might, if it's linear, you put it into a matrix, you plug that matrix into Octave and you row reduce, right? So that's something that we could do. All right. So everyone's good on that, hopefully? Okay, same function. Okay, but I'm going to change the question now. So just like when we were doing single variable calculus, right, you had to find the critical points, and then you had to classify the critical points. You had to figure out, are these maximums, are they minimums, are they saddle points, whatever the case could be. So this is the same function. Okay, so you already know what the critical point of this thing is. And now I'm asking you to classify it, right? Tell me, is it a maximum? Is it a minimum? What is it? Yeah, exactly. Or you can find the eigenvalues if you really want to, but because this is a 2x2 case, there's that tricky determinant thing that we can do where we don't actually have to find the eigenvalues because we know that's actually, that's a fair amount of work. Shouldn't need octave for this one. You can use it, like if you really want to. That's not a terrible idea, but there is a test that you can do here, right? Or if you didn't have octave. So this is the sort of thing. It's true. Now that you have octave, it really doesn't hurt. But back in the in-person days, you would have had to do this one by hand. Okay, sure. Well, now's a good time as any to start studying, the linear algebra that we're going to need. I'm going to lock this up in 30 seconds. It's looking good though so far for those of you who have responded. Lots of right answers in there, which is pretty good. Right. Though in a 2x2 case, remember there's a formula for the determinant, right? It's AD minus BC. You multiply the diagonals and then you subtract the product of the off diagonals, remember? So like what you're doing is Lagrange's expansion of the determinant formula, but in the 2x2 case, it's not super necessary like to use this minors approach. Or you just plug it into octave and det is a thing, is a function in octave. Okay, majority of the class is B. That's phenomenal. B is absolutely the correct number, the correct answer. And so we're really going to reuse some of what we have here. And so if we want to classify the critical point, this case, we don't have a first derivative test. That doesn't make sense. But what we do have is a second derivative test, right? So what we're going to do is we're going to compute the Hessian and we're going to look at its eigenvalues. So we don't have to do that in this case because it's a 2x2 matrix. Okay, so first thing, let's find the Hessian. Right? Which we know is the matrix of second order partial derivatives. So I'm going to compute that very quickly for -1, -1, 2, like this. Okay. Now, if you really want to, you can go into, so remember, the general test for this, if you don't have a 2x2 matrix, the general test is to find the eigenvalues of this matrix. And if the eigenvalues are all positive, then you are a minimum. If the eigenvalues are all negative, then you're a maximum. And if you have some sort of mix of positive and negative eigenvalues, then you are a saddle point, okay? So just out of curiosity, I'm gonna go, because I didn't work this ahead of time, but yeah, the eigenvalues are like 1.5 and 4.4, right? So they're both positive. So we expect this to be a minimum. And if you were to plug this into octave, that's what you would get. But there is another test, right? And this test really only works in the 2x2 case, but there is another test. That test is to look at the determinant, right? So the determinant So let's say if we're computing the determinant, right? So we get that the determinant of the Hessian, well, actually, you don't just want to do it in general. In this case, it's kind of constant, but yes. Oh, there's two guests in the room. You can't see the other one. But you actually want to plug in your critical point at this point. Now, obviously, it doesn't matter in this example because the Hessian is actually constant. But normally you would plug this in and then you would compute its determinant. So in this case, we're going to get 4 times 2 minus -1 times -1. If we do that, what do we get? We're going to get 8 minus 1, so that's equal to 7. Okay, and that's positive. So because it's positive, now what we do is we look at the fxx derivative, okay, the 1, 1 element of this matrix, right? And the test is that if this number is negative, it's automatically a saddle. You're not worried about this, okay? So if it's negative, you just like, yeah, it's a saddle point, who cares? So what we're going to do then is we're going to look at, because it's positive, we know we actually do have a max or min, and then we look at this number right here. And if it's positive, it's a minimum. If it's negative, it's a maximum, right? So let's say since the xx partial of f at 1, 4 is equal to 4, which is greater than 0, xy is 1, 4 is a min, okay? And again, another way that you could do this is to compute the eigenvalues. So alternatively, right, the eigenvalues are both positive. I don't know exactly what they are, but I went and I plugged them into Octave and I got 2 positive numbers, right? I got like 1.5 and 4.4, something along those lines. So boom, I know I'm in a good situation. Both, if all your eigenvalues are strictly positive, you are a minimum. If they're all negative, you're a maximum. And if you're a mix, you're a saddle point, okay? So if you were given a 3x3 matrix like this on your final exam, you do the same sort of thing. You throw that into Octave and you figure out what your answer is, okay? So this test, again, this test that I did with the determinant and then looking at the xx partial, that only works for a 2x2 matrix, okay? You can't use that test for a 3x3. Same thing, if for whatever reason, you don't want to use the xx partial, the thing in the top left-hand corner, you can also use the thing in the bottom right, okay? So you can use the yy partial and same sort of thing. That will also tell you the answer. Okay, so I said, can you go, so first question was, can you do determinants again? So I mean, the determinant of the 2x2 in this case, yeah, only xx and only yy. You can't infer anything from the mixed partials, the xy and yx. You don't know anything about that. So in terms of the 2x2, you get AD minus BC, right? And then when you do the, what do I want? When you do the 3x3, 4x4, or whatever, you do that minor thing where you delete a row and a column and compute the determinant of the minor and do those sorts of things, right? Can we use Octave in the finals? Absolutely can. Can I do the eigenvalue method? I'm gonna say no for this one, just because computing eigenvalues does actually take a really long time. And there's sort of other things that I want to get to here, but what you could do is use this as an example to practice your eigenvalues when you do linear algebra stuff, right? And just go ahead and confirm that you actually do get 2 numbers. Also, I don't think we designed this problem to make sure that the eigenvalues weren't horrific. So it's quite possible that the eigenvalues need us to use a quadratic formula, which just makes them even worse, right? But use it as a sample thing. And then if you want us to check your work, throw it up on Piazza, and we're more than happy to do that. But yeah, I don't want to spend too much, like if we did the eigenvalues, we'd spend most of the class doing it. I don't want to spend too much time doing that because there's some other things I want to hit. Okay, so which one do I want to do now? Okay, let's do this. Listen, we just did a question like this here. Maybe let's pivot into this. Okay, so we've got this function. We've already told you 1, 1 is a critical point. So you don't actually have to solve for the critical points, right? I just want you to classify this thing. So it's the exact same thing that we just did. Go ahead, find for me the Hessian, and then apply the same test, or throw that matrix into Octave and ask it for its eigenvalues and see what it gives you. Eig, EIG is the function to tell Octave to do eigenvalues. It should be, yeah. Yeah, so the question is the code for finding eigenvalues on Octave up? Yeah, it should be in Quarkus. I think if you go to the like syllabus portion, it's in other, it might be in materials. Let me see. Yeah, it's in other. So go to the other tab, and then there's something called the Octave cheat sheet in there, which you can download, and it sort of gives you what those commands are. Okay, 30 seconds. Okay, so let's take a look. Majority of the class says B, that it's a minimum. Absolutely, B is, or our critical point here is a minimum, so good job. Let's figure out why. So even though in this question, we've already sort of been given what the critical point is, we still have to compute the gradient, right? Because we need to compute the Hessian. In order to compute the Hessian, we have to compute the gradient. So this is question 4. So we're given f of xy is xy plus 1 over x plus 1 over y. Okay, so let's compute the gradient of this. So computing the gradient. So we get the gradient of f xy. So we're going to take the x partial to begin with. So we're going to get y let's say minus 1 over x squared. And then, the equation is completely symmetric in x and y. So even if you like didn't want to go through all the motions again, you can basically just switch x and y. You get the right answer. Like so. Okay. So that's the vector of first derivatives. Now we need to compute the Hessian. So now the Hessian. So we get HF x, y. And of course, at this point as well, you can double check that your number is actually a critical point, right? Like if you plug x, y equals 1, 1 into your gradient, you do in fact get the zero vector out. So that's a good sign. So now if we compute the Hessian, so we need to take the x derivative of the x derivative. So what does that give me? That gives me 2 over x cubed. Now, if I take the y derivative, I get that. And again, this should be sort of nice symmetric matrix like so. Okay. Now, again, we're actually trying to, so this Hessian applies for all points. So, but in this particular time, we're trying to figure out what the classifying the critical point 1, 1. So we're going to plug 1, 1 into this function. 1, 1. That gives us 2, 1, 1, 2. That's a really nice thing. And again, you can go and you can compute the eigenvalues of this if you want, or we can apply our test where we compute the determinant, determine if it's positive or negative. So let's say applying our test. So we're going to get the determinant HF1, 1. So that's the determinant 2, 1, 1, 2. So what is that? That's 4 minus 1. So that's 3. That's positive. So we definitely have a max or a min. Then we look at, again, this number here. We say, oh, that's positive as well. So this is a minimum. So since di(x(f) 1, 1 is 2 greater than 0, xy equals 1, 1 is a min. Okay, any questions about that? Everyone's good? So again, there's a little bit of work here, right? We had to compute a second derivative, and we know that second derivatives can be a nightmare to compute, even when we're functions of one variable, let alone when there's, a whole bunch of the bloody things that we have to compute because we're dealing with multiple dimensions. And you can imagine that in the 3x3 case, this even gets messier. Okay, so let me give you one more example, because only 53% of the class got this one right. So where do we apply this knowledge? I mean, optimizing multivariable functions is, again, one of the main applications of calculus is optimizing multivariate functions. Because again, most life actually occurs in multivariate calculus, right? Like you have multiple dimensions that you're working in, and being able to find maxima and minima, all of life is a max and min problem. Literally all of life. Yeah, you could become a professor teaching multivariate calculus. That's definitely an option. But seriously, all of life is a max and min problem. Like literally everything that happens, right? You're always trying to maximize something. You're always trying to minimize something. And in fact, all of nature operates on maximum and minimum principles. So being able to find maxes and mins is super important, but it's generally really, really hard. In fact, there are entire fields dedicated to optimization. If any of you ever get a chance to talk to TJ about it, I think his PhD was in nonlinear optimization. Like that's what he was, he did an applied math PhD. So his PhD was in trying to make things as big and as small as possible, and how hard that is as a general rule. So, multivariate calculus really unlocks a bunch of tools that allow us to do that. And that's super, super important, right? Yeah, basically everything is PDEs. Everything is that sort of stuff. Why did we only find 4 minus 1 equals 3 and the xx derivative? So that is the test that we can apply in the 2x2 case, right? So you compute the determinant. If your determinant's positive, you look at the xx derivative. If that's positive, it's it's a min. And if it's negative, it's a max, okay? How can one have the brain capacity for this? It's not too, here's the thing, Okay, and here's something you're all going to learn very quickly. Everything you think is hard this year, by the time you guys finish second year, you're going to look back on this stuff. You're going to like, that's easy. Second year stuff's super hard. And then you're going to go and you're going to do third year stuff, and you're going to look back at your second year and you're going to be like, second year was super easy. It's the third year that's hard, and so on and so forth. And the reality is that this just keeps continuing forever. Right? So for me, this stuff is very straightforward. There's no expectation that it should be straightforward for you, right? You kind of need to progress a little bit more, but eventually this stuff will be easy. But that stops after, it does. I mean, if you spend enough time doing anything, you'll get good at it. Listen, tell me that there wasn't, I don't know, maybe you guys don't remember this, but there was a time I legitimately remember thinking that tying my shoelaces was going to be tough. You know what I mean? I remember the first time I learned to tie shoelaces, and I struggled with it a little bit at first, and then it took practice to get better. And I really think I promise you, as funny as I think it would be, I no longer struggle to tie shoelaces. Okay. I don't have Velcro shoes anymore. And the reality is that just became simple, right? You know what I mean? You do anything enough, and as you do progressively more difficult things, the previous stuff gets easier, you gain more insight. So this stuff for you might seem difficult now, but if you continue on to do this stuff, it becomes much, much easier. And you look at me with wonder now, but it will be true. In a couple of years, you'll look back on maybe not this stuff, because if you don't go do more math, you don't kind of progress beyond that point. But for those of you doing like management, accounting, economics, I'm certain you'll look back at your first year material and you'll be like, it wasn't that bad. It's just because you're in first year, right? It's your first exposure.
For me, the big experience from what you're talking about was driving a car. The first time I ever drove a car, I'm like, there's no way I'll be good at this in my life.
There you go.
And, no, it's just a second nature. You just do it.
That should be everything, right? Like, I mean, I don't know about you guys, but like the first time I was typing, right? Like, home row and all that, I thought that was a nightmare. I was like, there's no way I'm ever going to be able to figure this out. But of course I did, right? And so we're all like that. And, it's important to have that growth mindset, right? To believe that you can learn and to know that you can learn and to have that confidence so that you can, right? And you can push it to the next level. Reaching the 0.1% of the entire math field knowledge, Connie, there might actually be a sense in which that's true, but what you learn very quickly is that like 0.1% is still really, really big. Do you know what I mean? Like, yeah, exactly. Yeah. Of the people in the world, you guys already know more than 99% of the world. Do you know what I mean? In terms of mathematics, like legitimately, that's probably true. But that 1% is really, really big. So let me put it this way. I always say I'm in the top 1% of hockey players, but you know what? That still leaves a lot of people who would absolutely kick my ass at hockey. Do you know what I mean? Like it's something I love to play and I'm decent at it, but like, and that puts me in the top 1% just because if for nothing else, most of the other world doesn't play, but it doesn't mean that I'm anywhere near the best. Do you know what I mean? So it's one of those things that you should take pride in that, in being in that 1%, but also keep in mind that that 1% goes much deeper than we think. Then we kind of like 99% sort of betrays how deep that pool really is. So, just kind of keep that in mind. Jeremiah, let me talk about that maybe a little bit later about what I did my PhD in. But I mean, it's just a bunch of words to you guys, right? It wouldn't make any sense. So Natalia, sure, remind me maybe closer to, the reality is I might not be able to, Natalia, just because that question is so specific that there isn't anything like it. I'll try. Remind me at office hours, okay? Sure, yeah. It's actually like, it's not too hard. First of all, I'm certain that there are a lot of you who are very gifted at some things, and that's super cool out there. But it's actually not hard to be in the top 1% of stuff, right? It's just because most people don't do it. Actually, let me just write that down quick. Now, let me throw up another question here. I really want us to practice this sort of thing here. Finding critical points, solving nonlinear systems is a ton of stuff that we're going to do on Thursday. Okay, so we're going to do that a lot. But I want to give you another question here. And this time, I'm even going to give you the Hessian. Okay, so all you have to do is apply this. So let's see, have you learned what it is that you're supposed to do, right? So let's go and let's do this one. Okay, now this is scary because like there's a lot of stuff on the page, but don't worry about it. Okay, so I've given you this function. I've computed the Hessian for you. And I've said classify the critical point 0, 0. So the question now is, did you understand the last two questions, right? Do you understand how to classify a critical point from the Hessian? So I've given it to you here. You tell me what to do. Same, sure. It might be Rafid. I'm not 100% positive. It sort of depends on how quickly we manage to get through it. There could be another one. Also, for anyone who finishes this 1, -1, here, maybe let me put that in there. So it's maybe like a bonus here. Let me. So as a sort of like bonus here, okay, 1, -1 is also a critical point. Okay, classify it. So that's sort of like, you know, if you run out, you answer this question really, really quickly. Oh, I need to relaunch the polls. Then you can try it with that critical point as well, and just make sure that you really understand what's going on. That's, you know, like your exponential, like your usual e to the x thing. But so basically that term, it's like scalar multiplication of matrices. That term actually needs to be in all 4 parts, but it's common to all 4 parts. So we factored it out of the matrix. Yeah. It's up to you, Brandon. Like, yes, as a general, it does need to be part of your calculation, but in this case, it reduces pretty quickly. And in fact, you can see it's really not going to affect, right? Like the exponential is always positive. So it's not going to affect the sign of the determinants at all, right? Because that number is just always positive. So you're to put it into every single term, it doesn't change the sign of anything. And it never will, right? There's no value of x or y where the sign of this thing would change. But yes, normally you would have to include it. Mm-hmm. Yep, Connie, exactly. And I'm going to lock this up in 30 seconds or so because, yeah, exactly, Sam. So it's like, you remember everyone here, let me maybe write this in here. So we learned when we learned matrices, and it's been a while, but we learned that we could do something like this, right? C is a bad choice. Let's maybe make this, that's, I don't know what that is. Let's say gamma. A, B, C, D, right? That means gamma A, gamma B, gamma C, gamma D, right? So it's like scalar multiplication, and you can just multiply it into each term if you want. Now, again, in this case, it doesn't actually end up mattering, especially for the critical point 0, 0, because if you compute that number ahead of time, you see it reduces to, you know, be a really nice number. But yeah, because it's positive, it actually doesn't affect things. But yes, you do actually have to include it. Okay, so let's take a look at this. All right, Majority of the class says C. Phenomenal. Absolutely. Yeah, the answer is totally C. Let me just get rid of that stuff. So this is question 7. And we're told that, oh, this is kind of gross to write down, right? But we get e to the negative x squared plus y squared divided by 2. This function is even really close to the one that you were given on your assignment, right? It's really, really close. xy, 3 minus x squared minus 1, 1 minus y squared, minus 1 minus y squared, and then xy, 3 minus y squared. Okay, now I'm going to copy that because we'll probably just kind of do the bonus while we're at it. I'm going to just copy that. Okay. So remember what we have to do is we have to plug 0, 0 into this, right? Don't compute the determinant from here. It's going to be some big ugly function with lots of x's and y's, not very pretty. Okay, so I generally don't recommend doing that. But instead, let's plug in 0, 0. Now, the great thing about this exponential on the outside is that when we plug in 0, 0, we just get e to the power of 0, right? E to the power of 0 is just 1. So, we're not worried about that at all. So that just becomes 1 times. Now, we plug 0 in. Oh, that's very nice, right? The diagonal terms just become 0. The off-diagonal terms become -1 times 1. So it looks like both of them are going to be -1, right? So that just gives us 0, -1, -1, 0. Let's compute the determinant of this. So applying the test, right? We get the determinant HF 0, 0 is going to be 0 times 0 minus, be careful with your minus signs here, right? You don't want to get burned. You get -1. Because that's less than 0, it tells you you have a saddle point. So 0, 0 is a saddle. Okay. Again, if it were positive, then we actually would look at the signs of the XX element, but it's negative. So that tells us saddle. Now, did anyone do the bonus? So if you do the bonus, what do you get? All right, so for the bonus, we said 1, -1 is also a critical point. Okay. Min? Everyone get min? Let's find out. So we get 1, 1. Again, we've got to plug it in. So we're going to get e to the -1 plus 1 divided by 2, whatever that number is, right? Times, here, maybe let me again just sort of paste this in here so we can see it. Hey, why didn't my things copy over? Okay, stupid thing. All right, here, let me look up here. 1, 1, so we get 1 times 1 times 3 minus 1 squared. 1 times 1 times 3 minus 1 squared. Then we get 1 squared minus 1 times 1 minus 1 squared. Okay, and if we do all that, what do we get? So we get e to the -1. This to me looks like 2. This to me looks like 0, 0, 2. Does that look right? Why is it 1 at the outside bracket and 0 at dxx? Like here, like why is that 1? So let's plug 0, 0 and we get e to the -0 plus 0 divided by 2, right? That's e to the 0, that's 1. Right? Yeah, no, this is for the previous question. The question I was asked is for the previous question. So I've just scrolled up really quickly. And then if you plug 0 into this, right, you get 0 times 0 times 3 minus 0. So that whole thing is 0. Right, so you just plug everything in and see what you get. Okay, so we get this thing. What is the determinant of this? And I actually, Oh yeah, sorry, you're right. It should be -1. Ah, you're right. You are right. So this should actually be -2, right? Sorry, thank you for that correction. Like that. Good catch, Agam. Thanks for reminding me. So the determinant of this is going to be -2e to the -1 times -2e to the -1, right? Minus 0 times 0. So that gives me 4e to the -2. That number is positive. And then I come up here and I say, oh, okay, is this positive or negative? This one's actually negative, unlike our previous example. So this one's actually a maximum. Unless you make the mistake like I did, right? And forgot the minus signs. So you see, even I get burned sometimes on those minus signs, right? Kind of. So -1 is a max. Does that make sense? Everyone see how that happened? Any questions about that? Okay, I assume that we're good. Give me like a minute and a half, just refill my water and stuff, and I'll be right back. And then we'll go into office hours and I'll answer all your questions.
I'll be here till you're back, Tyler.
All right, sounds good. Thanks, man.
I don't think we asked this question at the beginning of class, but how did you guys find the test last week on Thursday and Friday? Question 2 was tough. Pain. Anyone found it relatively straightforward? No, question 3. What was question? Question 3 was the one with 1/n, right? It was like the areas under the curve, but the function itself had like a constant that changed with that could change, that 1/n component. Yeah, right, something like that. I mean, honestly, that one wasn't the worst. Like if you tried it, like what you could have done to make it easier theoretically was use a couple examples for n. I know a lot of people use n equals 1 as an example just because it's the easiest, because it removes the denominator. But I would have rather used like n equals 2, 3, or 4, just because you would have actually seen the gap changing. Because n equals 1 would be like a kind of a regular absolute value function, and n equals 2, 3, 4 is going to kind of start increasing, right? So that would have showed you better on how the function will behave under the curve. The hard part about it was actually like once you differentiate, it looks hard, but like it wasn't that bad, mainly because like n is a constant, right? So when we differentiate when we integrate a constant, it just becomes the constant multiplied by a variable, right? So a lot of it just is like very simple integration because it's all power rule. The 1/n becomes like 1/n times x, and so on and so forth. Yeah, so like the question was, as n increases, does it get closer to 1? Yeah, basically that's what's happening. And you could test it out actually. It wasn't really that hard. Like you could have just tested it out with numbers. Like try first like n equals 1, and then try like n equals 10, and then n equals 100, and so on and so forth. If you just did that as like a scratch work on the side, you'd see the kind of the V kind of flatten out time and become like a flat line. But
Talking about the test, eh?
yeah, question 3 they were asking, but they're saying question 3 was really difficult.
I think like the hardest part about question 3 was probably the intercepts, right? But like
I think that's not even the worst. I think it was like as long as you realize that V was going to get flattened out by putting some examples, I feel like after that became a little bit straightforward.
And yeah, how many of you actually plugged that into Desmos? Because 100% I wanted you to plug it into Desmos. In fact, I was talking to the instructors. I'm like, should we do it in Desmos ourselves and then put like a QR code in the test so that students can scan it and like pull up a Desmos thing? But we 100% wanted you to do it in Desmos, because if you put it in Desmos, you can actually see what's happening. In terms of, yeah.
There's a quick thing. I'm just gonna head out to start the
Okay, see you later.
Yeah.
So in terms of like finding those intersections, because if you do it, it's a quadratic formula, right? You kind of have to do that. But in practice, and once you guys see the solutions, and I'll post them pretty quick here. When you see the solutions, I would have been 100% fine with you just saying, hey, look, f of 1 is 0 and all the GNs f of 1 is 1 and all the GNs at 1 are 1. So that's where they meet. And then you don't have to quadratic formula it, right? You had to include something sort of specifying where the bounds were, but like that's all you had to do. So you didn't actually have to do the quadratic formula if you wanted and totally use Desmos, okay? Otherwise, you have to do a quadratic formula. You have to actually solve, x squared is equal to 1 minus the absolute value of x over n. And you could do that, but yeah, you do actually get, you can actually determine that the intersection point is at x equals 1. But again, you could have just plugged it into Desmos and used that to be like, oh, hey, look, that point actually isn't changing. So we can do it that way. And that is what I wanted you to do. Okay. So some of you ask, hey, am I allowed to use Desmos? Again, it's like Octave. Not only are you allowed to use it, I want you to use it. Okay. There's nothing wrong with using software to help you get an understanding for a question. You can't use it to solve the question, but using it to help figure out what the heck's going on, that's totally fair game. And that happens in real life too, right? You imagine you're given a problem to work on. No one's going to say, no, you're not allowed to use software to help you, right? And so you totally should. You use whatever tools are available to you. Again, not cheating in this case, but use whatever tools are available to you in order to help you figure out what the answer is. Okay, so I want you to use Desmos. I want you to use Octave, and figure out how to do these questions. Right? There's nothing wrong with that. Okay, that's one of my objectives. I want you to be able to do that. And then, so the interesting thing to me here, it seems like nobody said question 1 was the hardest, right? Maybe because we kind of trained you how to do it, right? Like we did it a ton in office hours. We had an assignment question to do it. So nobody thought question 1, it sounds like, was hard because we had just done it so much. Is that fair? Like everyone had a good idea of how to approach that? Oh, right, you did say that. Yeah, okay, but you're saying parts 1 and part 2 were fine? We did have something, right, yeah, okay. I mean, we did have something like that. We had just a little twist, right? Just a little twist to see if you can do it. And I think a couple of you picked up on it because the integral goes from 0 to 12, right? But we only give you the graph from 0 to 6. So it's kind of like, do you remember? So you're even saying to me, Kelly, like you didn't like the x over 2, right? Or the g of x over 2. And so that again is sort of like a hint that, substitute away the things you don't like. Do you know what I mean? So, same thing when we were doing, I think on Thursday, we were doing a problem. I saw this e to the x squared and I said, I don't like that x squared up there. I'm going to make it disappear by substitution. And that is a thing that you can do, right? So yeah, that one might have been a little bit trickier, but that's okay too. And Kelly, everything else was okay? Hopefully it wasn't too bad. Okay, yeah, that's good to hear. If every now and then there's a small part of one question that, gives you some trouble, that is, I think, okay, right? I mean, it's great if the whole test is easy for you, but if every now and then there's a little part that's a little bit tricky, I think that's okay. Okay, so I was asked, so Natalia, you wanted something like the assignment, right? Like 1, 2, 1, 3, if I recall correctly. So with the integrals, just keep the integrals. Okay, so like in part 3, notice how the integrals show up in the answer, right? Because part 3, we actually give you what the answer is. And notice that the integrals are still there. Do you know what I'm saying? So literally just don't do anything with the integrals. Like treat them as a number. In fact, if you want, make the integral disappear. Like call that integral, capital I, and solve the linear system with capital I in. And then once you get the answer, replace I with your integral. Do you know what I mean? So like, I really don't even worry about what that integral is, because we just kind of keep it and let it hang around as we go. Okay. And then, so part two, did you say part two is bugging you too? Okay, and then 1.4. So 1.4, so in 1.3, you solved for capital F and capital G, right? And we give you the answers there. So we say f of x is equal to 1/2 stuff in brackets. G of x is 1/2 stuff in brackets, right? Okay, now in part one, you showed that u of t comma x was equal to capital F of stuff plus capital G of stuff, right? So, or actually we even say that in part four, right? U of t comma x is f of x plus ct, g of x minus ct. So here, actually, let me maybe just share my screen for that. Right? So we tell you f is this thing, g is this thing, and then u is this. So what we want you to do is really just take these two equations, plug in x plus ct, plug in x minus ct, and you'll get this. Do you know what I'm saying? So it really just wants you to take this thing, plug x plus ct into this expression for f, plug x minus ct into this expression for gt, and then add them together and simplify. Yeah. And you should get this, right? Like we've double checked this a bunch. You will get this answer, because there's going to be a bunch of cancellation here. You can kind of see it, right? Like there's going to be a bunch of cancellations that happen. You get your f of a minus g of a, your negative f of a plus ga. You add those things up, those constants are just going to vanish. And yeah, that's what you got to do. How to even start like this part, like how to start part one. Okay. So what do I want to say? It might help to write this as so I mean, this is definitely a chain rule problem. Do you see that it's a chain rule problem? Because you've got a function, you've got a composition of functions, right? One function is x plus ct, the other function is capital F. So what you're going to want to do is you're going to want to chain rule this, but maybe it'll help if we write it in a slightly different way. So let's do it like so, right? So what we're trying to do is we're trying to figure out how to differentiate, something like this, die x, f of x plus ct. Okay, so I think sort of the key that's going to make your life a little bit easier here is let's maybe call y a function of a different variable. So let's say w is f of y, right? Because it doesn't matter what number, like what letter you plug into a function. It's just a name, right? And then let's call a g of x t x plus ct, right? And that's y. So when I do this composition, I get f of g of xt is f of x plus ct. Do you know what I'm saying? Does that look fine? Okay, so let's draw our dependency tree. So at the top of our tree is our dependent variable, w. What does w depend on? What variables? Like directly beneath it, right? Like what directly does w depend on? Eventually, w will depend on x and t. But remember, when you set up your dependency tree, you're just looking at the next line down. Namir, yeah, that's absolutely right. Though, like in this case, we're kind of writing it in terms of their variables. And right, exactly, why? Or as was kind of pointed out, it depends on y through the function f, right? Okay, what does y depend on, right? Look at this equation. What variables does y depend on? Remember, c is a constant, right? Exactly, x and t. Okay, so if we want to compute die w by die, let's say x, what is that going to give us? And you can just like, if you're typing it in chat, just write dw, right? Don't try and make it curly d. Right, exactly. So yeah, exactly. So I don't want to write it down because I don't want to spoil it, but yeah, that's absolutely correct. Christian, yeah, and you'd probably want to multiply those, right? Just to be clear, right? But you want to multiply those. Okay. And you know what the first of those things is through this, right? And you know what the other one of those things is through this. Does that make sense? Okay, so what do you get if you do it? I want to make sure that you get the right answer. And then your answer shouldn't have any W's or Y's in it, just in terms of like F. So what do you get if you actually compute that? And again, anyone can participate in this too, right? Even though I'm talking to one person here as a direct message, if you want to do the exercise as well as I'm doing it, please send me a direct message and I'll confirm that you've done the math correctly, right? You don't have to just watch me talk to somebody else. Yeah, Agam, beautiful. Okay, now translate that into some statement about F's and such, right? So replace your first term there, right? Look at one of the circled things. What, if you were to place that derivative with F's and stuff, what would it become? Ooh, close, Natalia. Very, very close, right? But don't forget, there should probably be a derivative in there, right? Like dw dy. It's very close. I think you see that there's a 1, but you're missing your like dw dy. Do you see what I'm saying? It would be neither, right? So that equation is the equation which describes how w and y are related to each other is this, right? So, kind of think about single variable calculus. If I said if y was equal to f of x, dy dx is f prime of x, right? So all I'm doing now is kind of changing notation. So what's dw dy? Yeah. Okay, so write out the whole thing for me though. I just want to make sure that we're on the same page. So what is dw dx? And Natalia, do you see how to fix it? Ooh, okay. Why did you write the 1 over part there, Kelly? Can you explain to me where the 1 over, your denominator, like where'd your denominator come? Or actually put brackets in there so I know. I assume that That whole thing is the denominator, right? Natalia, what do you mean add it? Like you want to multiply those two terms for sure, right? There shouldn't be any addition there. Right, okay, now Brandon, but your answer has to be in terms of x, right? So sub y back in to that answer, right? Y equals x plus ct, and that's your answer, right? Because if I'm asking you for dw dx, your answer needs to be in terms of its final thing, right? Just like when we do the chain rule, right? We say d dx f of g of x is f prime g of x, g prime of x, right? We have to sub the g of x into f prime. Yeah, exactly, Natalia. So you multiply. Now you know what, like, oh, I see what you're asking about the next term. No. Yeah, we're just computing dw dx, right? So yeah, don't worry about the t. The t is not important, right? Not right, Brandon. The derivative of x with respect to what, Kelly? Okay. All right, let's try a different exercise. Okay, so let's say I give you the function. Let's make something up here. E to the x squared. Okay, and g of x comma t is x plus ct, right? So if I do this composition, I get e to the x plus ct squared. Now, we don't have to use the multivariate chain rule in order to do this problem, right? Because we actually explicitly know what all the functions are. Okay, sure. So Sam, tell me when you're back then, okay? So we don't actually need the multivariate chain rule in order to do this problem, specifically because we can just, we explicitly know what all the functions are here. So I now have my function of x and t, and I can just compute its derivative. So if I compute the derivative of this function with respect to x, I get the following. So I'm going to get 2x plus ct e to the x plus ct squared. Does that look right? Okay. All right. Now, if I were to just differentiate these two terms separately, or maybe, you know what, maybe let me call this f of y, just to sort of be consistent with what we were doing above, okay? So I know that f prime of y is 2y e to the y squared, right? I know that g prime, or di g by di x, xt is equal to 1. So this is the same thing do you see what I'm saying? Like, notice that, right? First of all, my answer can't be in terms of y's here. It's got to be in terms of x and t. But how did I get this? Well, everywhere there was a y down here, I plugged in x plus ct. And then I did technically multiply by this, but just in this case, it's 1, right? So it's kind of boring. Does that make sense? Everyone, do you see like what I'm trying to say here in terms of how to do this problem? Okay, good. Right. And so, yeah, I think it's important as well, everyone, to remember when we write, and I'm pretty sure I said this in the video, when we write something like this. So again, let's say that I have this chart instead, okay? Obviously, this isn't related to the problem, but I just want to give you an example. Is it, right, sure. But I mean, play with it where there is an explicit function until you're comfortable moving to the next level of abstraction. Do you know what I mean? So if that abstract function is bugging you, give it a function, right? Like choose something explicitly and play around with it a little bit until you get a feeling for how it should work, right? And then that hopefully will lead you to be able to say, okay, well, now if I was going to abstract it, how would I do that? So let's say you were asked for dw ds, right? So we know that's dw dx, dx ds plus dw dy, dy ds. Now, when I write this though, okay, I'm cheating because this is just sort of shorthand. What I need to do when I write dw dx, I'm making sure that I actually write this as a function of s and t. Right? Just like in the single variable chain rule, remember you have to plug the inside function back in, right? Up here. Or d dx f of g of x is f prime g of x, g prime of x, right? You have to plug that inner function into the outside derivative. So we have to do the same thing here, okay? Once we've computed that outside derivative, you still have to evaluate it at the inside function. So just be careful about that. Because your answer in this case entirely has to be in terms of s and t. Do you see that? Does that make sense too? Does that help? All right, and we usually, when we write Leibniz notation like this, we sort of omit the fact that we're evaluating the outer function at the inner function, but it's implied there, right? We can't forget that. Okay, maybe let me give a single variable analogy, right? If we have y equals f of x and x equals g of t, then we say dy dt is dy dx times dx by dt. But again, implicitly, right? This thing here, that's your dy dx, right? But it is evaluated still at the inner function, right? It's not just f prime of x, it's f prime of g of t, right? So even in Leibniz notation, which is sort of, again, a shortcoming of the notation, but even in Leibniz notation, when I write dy dx in this equation, I mean that it is evaluated at the inner function. Okay. Any questions? Okay, Kelly. Yeah, yeah. Though, hold on, your brackets are a little bit weird, right? So first of all, again, remember your answer shouldn't have any y's in it. And then I'm not certain why there is still a c and a t in there, right? Like what is the derivative with respect to x of x plus ct? Remember, t is not, this isn't implicit differentiation, right? So the derivative of t with respect to x is 0. Does that make sense? Does that help? Right. Right, so this is just equal to 1. Okay, great. And Sam, yeah, I see it. And then Kelly as well, remember your answer can't just, right, when you do dw dx, your answer has to be in terms of the very last set of variables. So plug back in the fact that you know that y is equal to x plus ct, plug that back into your answer, and then you've got the right thing. Yeah, no problem. Okay. So, Siam, so you're asking something about the Lagrange multipliers, another example question, right? Was it just like, no problem, see you later, Natalia. Can I go over it? Sure. Is there like a specific part? Because it has both an internal part and a boundary part. So is there like a specific part of that, or it's just sort of like the whole thing? Okay. So the question, so everyone, so this is from the Lagrange multipliers video. Another example, so the second one. All right, so it says find the extrema of this function, x squared y, basically on this set, x squared plus 2y squared is less than or equal to 6. Okay, and if you plot that thing, it looks something like this. Okay, so no, you are the next question. You're actually the only remaining question. We just had a test, so nobody cares. So just like when we do single variable optimization, we have to look at what the potential extrema are on the inside of your set, right? Normally, when we would do the optimization on an interval AB, we'd use critical points to do AB, right? The inside. And then we would just check A and B because these were the boundary points, right? So with Lagrange multipliers, we're doing the same sort of thing. So the first thing that we need to do is we need to check the inside. And the way that we can do that is with critical points and the Hessian, just like we did today. But then the way that we check the boundary, right? This part's the boundary. So we use Lagrange multipliers to do the boundary. Okay. So first things first, let's check the inside. And like I said, we just compute critical points and use a Hessian to do this, right? So this is critical points plus the Hessian. All right, so our function is up here. And if we compute the gradient of that, what do we get? We get, with respect to x, we get 2xy. With respect to y, we get x squared. And if I set that to be equal to 0, 0, that gives me these two equations. And from this, I get that x, from this, so from the second equation, x has to be 0. But if x is 0, both equations are satisfied, right? So y can be anything. And that is allowed. So that tells me that this entire line here is critical points. And this is something that doesn't really happen in one dimension, right? Where you get an entire critical submanifold. That's what this is called, a critical submanifold. But it can happen here. And so in this case, we do in fact get that the entire y-axis is a critical point, right? Okay, so now let's compute the Hessian. So we get HF xy is what? So we're going to get 2x, 2y, and then second function 2x, 0 like that, right? So, no, wait, something's wrong here. Oh, sorry, this should be 2y, 2x. I got these backwards. 2y, 2x like that, right? And now I want to look and say, well, what does it look like along this blue set here, right? This blue set is the set of 0, y, where y is between what? So if x is 0, y is between plus or minus root 3. Right? So I want to look at what this thing looks like. No problem, Kelly. See you later. Do you see how I got the root 3s? Does that bug you? Okay, sure. So what I'm trying to do is figure out like, what is this point and what is this point, right? Because these points are like the top and bottom of my chain. I guess I should just put less than here. So what I'm going to do is say, oh, well, this is the line x equals 0, right? Yeah, exactly. It's just within that circle. Or it's strictly speaking, it's an ellipse, right? So what I'm going to do is I'm going to take the equation x squared plus 2y squared less than or equal to 6, and I'm going to sub in x equals 0 into this. So I get 2y squared is less than or equal to 6, y squared is less than or equal to 3. So that tells me, actually, it should just be less than, because again, I'm only doing the inside, right? I'm not also doing the boundary. And that's how I get plus or minus root 3. Okay. So the Hessian is this thing. And if x is equal to 0, what do I get? So I'm going to get 2y, 0, 0, 0. This thing has determinant 0 because you have to do the boundary separately, right? Just like when we're maximizing functions on a closed interval, like the closed interval 0, 1, like you would look at the critical points in the open interval 0, 1, and then you check the boundary separately. So strictly speaking, we could do the boundary here, but like we're gonna catch it with Lagrange multipliers anyway, so we're not worried about it. But if you put less than or equal to, it's not a big deal here. This thing has, so this thing has, this is actually indeterminate because it doesn't have a, because it's determinant to 0. So, but on the other hand, f of 0y is just always equal to 0, right? So we can't actually at this point classify whether this is a max or a min. But what we'll do instead is we'll be like, oh, okay, the function f is just always equal to 0 on this set, right? If I plug x equals 0 into my function x squared times y, it's just always equal to 0. So instead of classifying it, what I'm going to do is I'm going to do now Lagrange multipliers on the boundary. And I'm going to say, okay, I'm going to find the max on the boundary. I'm going to find the min on the boundary. If any of them are bigger than 0, the 0 can't be the max. If any of them are less than 0, 0 can't be the min. So let's just remember that f of 0, y is equal to 0. And then we'll take a look at what we get when we do Lagrange multipliers. Okay. All right. So for now, for Lagrange multipliers, so we've got f of x, y, just as a reminder, this is x squared y. And we've got our boundary function is x squared, what is it? X squared plus 2y squared minus 6. Right? And you see how we got the boundary function? Right? We take this equation, x squared plus y squared equals 6, and then we just make that whole thing equal to 0, right? And that's our function. So that's just how I got that, right? Lagrange multiplier says that there is some lambda, such that the gradient of f is lambda times the gradient of g. Okay, well, we already found the gradient of f. Right, we said, what is it? It's 2xy x squared. The gradient of g, it's even easier. It's 2x 4y. So setting these two things to be equal, we get 2xy is lambda times 2x. And then we're going to get x squared is lambda times 4y. Okay, this is our nonlinear system of equations. If we also include this, we now have 3 equations. We've got 3 unknowns. x, y, and lambda. Okay, so we have to solve this. All right, and how do you solve this? So this is sort of where Lagrange multipliers gets tough. So we've got, so if I take this first equation, maybe let me number these. If this is 1, this is 2, this is 3. So if I look at equation 1, divide both sides by 2, I get xy is equal to lambda x, or I could write this as xy minus lambda x is equal to 0, or I could write this as x times 1 minus lambda is equal to 0. Now, the only way that's equal to 0 is if either x is equal to 0 or lambda is equal to 1, right? So either x equals 0 or lambda equals 1. So we break this into cases. Case 1, x is equal to 0. Okay, so if x is equal to 0, equation 2 becomes 0 is 4 lambda y, which implies either lambda equals 0 or y is equal to 0, right? Okay. And let's see. So now we're going to break this into subcases. Well, actually, yeah, okay. Well, let's call this case 1a. So y is equal to 0. This is not possible because now x is equal to 0, y is equal to 0, but equation 3 says that 6 must be x squared plus y squared, which must be 0 plus 0, and that's not possible, right? If lambda is equal to 0, we don't care. That really doesn't tell us anything. So case 1b, that's lambda equals 0. And now equation 3 tells us what? So equation 3 says that 6 must be equal to x squared plus y squared, which is equal to 0 plus y squared, which is equal to y squared. So y is equal to, oh, sorry, plus 2y squared. Plus or minus root 3. And that's what I was saying about, like, we didn't actually have to worry about whether y was equal to plus or minus root 3 because we catch it in Lagrange multipliers, right? So that's a possibility. So that gives us two solutions. 0 and negative root 3, and 0 and positive root 3. Okay, so that's case 1. So now case 2 is that if lambda is equal to 1, right? So now let's plug that into equation 2. So equation 2 says x squared is 4 lambda y. So we get x squared is equal to 4y. Great. Let's plug that into equation 3. So we're going to get 6 is x squared. Oh, why is my pen bugging out like that? Is x squared plus 2y squared. So that's going to be 4y plus 4y squared. And then, we can solve this quadratic formula, whatever it is. Right, so 6, well, here, let's actually reduce that. So we get 3 is equal to 2y plus 2y squared. You can solve this if you want, right? Figure out what it is from the quadratic formula. Do I do it in the video? Let's see if I can. Oh, sorry, did I miss a y squared? Do I plug in a y squared in there when there isn't a y squared? Oh, I think there might actually be a typo in, or a mistake in the video. Because I say that x squared is equal to 4y squared, and it's not. It's just equal to 4y. So actually, yeah, we'd have to use quadratic formula on this. So there's actually a small typo then in the video. So we get 2y squared plus 2y minus 3 is equal to 0. So now we have to quadratic formula this. So we get y is equal to negative 2 plus or minus the square root of what? B squared minus 4 times 2 times 3 divided by 2a. So that's 4, right? Oh, 2 times 2, -3. So that's -2 plus or minus what? So we're going to get 4 plus 8 times 3 is 24. So this is 28 divided by 4. Can I pull a 4 out of that? I can. So this is going to be -1 plus or minus root 7 over 2. And so that gives me 2 more solutions. I guess I need to figure out what x is from this, right? So now we know that x, so from equation 1 then, what is equation 1? 2xy is, okay, well, let's just use this. So we assume lambda is equal to 1, so xy is equal to x. Oh no, that equation is already 0. We've already done that. So x squared, what do we get? X squared is 4y, right? So that's going to be -4 plus or minus, oh, I guess it'll cancel out the 2. So we'll get -2 plus or minus 2 root 7. So that gives me the solutions, -1 plus or minus root 7 over 2, or sorry, that's the y coordinate, -2 plus or minus 2 root 7. And there's your other 2 solutions. Okay, so like this is what we were trying to prep you for when we made you guys all do that numeracy question about solving nonlinear systems of equations. Like this is hard, right? And the reality is that the techniques and the tricks that I've used to solve this problem won't necessarily apply to any other problem that you've done. So you kind of have to just figure it out on the fly, which is why nonlinear systems of equations suck, right? Because you have to figure out what you're going to do as you're going. And that's really, really unsatisfying. Spilled everywhere. 1b, like case 1b. Okay, sure. Okay, so lambda was equal to 0. You're fine where the lambda equals 0 case came from? Right, because we have one of these two things has to be true. Okay, so at this point, what do we know? So at lambda equals 0, the reality is lambda equals 0 really doesn't do anything. We've already used equation 1, right? Equation 1 is how I got this case. Equation 2 is how I got this case. So under the assumption, in case 1b, we know that x is equal to 0 and lambda is equal to 0, okay? And if I come up to my 3 systems of equations, all right, so that one's done, right? I've used it. This one's done, I've used it. This is the only equation left, right? And I just don't, like, what am I going to do with it? So this equation luckily doesn't have any lambdas in it. So, okay, let me plug what I know into equation 3, right? And if this had lambdas in it, I would also plug in lambda is equal to 0. But the reality is this is the only equation left that I haven't worked with. So I'm just going to plug that in, everything I know in, and solve it for y. Case 2 is y is equal to lambda. It really shouldn't. Oh yeah, I do that. Wait a second. How did I get that case? Y is equal to lambda. Oh, son of a gun. You know what no, wait, what? Why didn't anyone do anything here? This is y, not 1. Right? Oh man, you guys got to yell at me. That's not 1 minus lambda, that's y minus lambda. So that actually, sorry, that changes the lambda equals 1 case to the lambda equals y case. And that actually does now, that does change this answer so that this is 4y squared. And where's my mouse? There it is. Good catch, though. Good catch, Christian. I was like, there's no way I made a mistake in that video, right? No, I made a mistake here. So 6 is x squared plus 2y squared. What do we say? X squared is 4y squared, so that gives me 6y squared. So that means that y squared is equal to 1. So y is equal to plus or minus 1, right? And then we said x squared is 4y squared. So that gives me just 4. So that implies that x is equal to plus or minus 2, right? So that actually gives now 4 solutions. So plus or minus 2, plus or minus 1. So yeah, good catch, Christian. Good point. But yeah, okay. So Simon, did 1b now make sense? Like you take all of this and plug it into equation 3. It's just one of those things is useless, right? Even though this is the case where lambda is equal to 0, it didn't really do anything because there's no lambdas in this equation. Mm-hmm. And for the record, lambda equals 0 is almost never a solution. Because, so this is case 1b, which means this is also true, right? We're still in case 1. All right, same thing. I use that in case 1a, right? I said, because x is equal to 0, x squared is 0. Yeah, exactly. Nothing happens for the lambda. Right. Yeah, it's not too bad. It requires like a lot of casework though, right? There's sort of no doubt about that. Yeah. Yeah. It usually breaks into a bunch of steps and you have to like just make sure you've got every single case down, right? It's just kind of annoying more than anything else, but that's nonlinear optimization for you. Like, or solving nonlinear systems, right? It's kind of big and messy. Right. Yeah, exactly. Exactly. So it's there's an argument here that it's about bookkeeping, right? Of keeping track of what cases you've done, what's true in what case, and that sort of thing. But best way to get good at that is practice for sure, right? And there's a good chunk of Lagrange multiplier questions that you can practice on and just get familiar and comfortable with solving. This is definitely a thing too that you should do with someone else, right? Like you each do it separately and then compare your answers and see if you missed any cases, because maybe your friend will get those cases, right? It's not that the steps are random, it's that there's no obvious place to start, right? So you want to sort of start with the place that you think is going to allow you to get into cases. So when I come up here and I look at these 3 equations, right? So I don't want to start here, right? Because I can't really say anything. There's no sort of cancellation or setting things equal to 0 or anything that I can do there, right? Same sort of thing with this. There's nothing I can do to start there. But I notice in this equation, there's an x on both sides, right? So maybe if I bring all the x's over and factor the x's out, that'll give me some cases that I can do. Do you know what I mean? So you have to look at your equations and say, okay, which of these is going to let me, figure something out? And in this case, in my opinion, the only thing that really works is equation 1. Now, that's not 100% true, okay? I could have done something else. I could have said, well, let's take this equation. And what happens if we just plug equation 2 into equation 3, right? So plug 2 into 3. Maybe I could have done it this way. So if I do this, I get 6 is x squared plus y squared. So that's going to be 4 lambda y plus y squared, right? All right, maybe I could quadratic formula from here. Why not divide? Suppose you can't divide. Okay, remember you can't divide because you don't know that those numbers aren't 0. Do you know what I'm saying? So you can never, ever, when you're solving these equations, you can't divide unless you'd make cases, right? If you make a case where you say case 1, lambda is equal to 0, and then solve it. And then you say case 2 lambda is not equal to 0, and then you want to divide by lambda, then that's totally fine. Do you know what I mean? But generally, you shouldn't divide unless you're certain that that variable is not equal to 0. Otherwise, you potentially might lose cases and you might lose information. So just be a little bit careful about that, right? Okay. And then, yeah, we could do something like, so from this first equation here, maybe let me just get rid of the 2's. The 2's are kind of pissing me off. So xy is equal to x lambda. And who knows, what are we going to do here? Again, if you break this into cases, then again, I might say, okay, case where x is equal to 0 and cases where x is not 0. If x is not 0, then you can cancel it from both sides and you get y is equal to lambda. And then you plug this into here. I guess this should be 2 lambda or 2y squared. But do you know what I mean? So did you see what I did right there where I said, assume x is not 0. Now y is equal to lambda. But then I have to do the x equals 0 case separately, right? And make sure that I've accounted for it. So what part of the boundaries? What do you mean by explain the boundaries? Because in my brain, there's a couple things that could mean. Sure. Mm-hmm. Right. So basically, that comes from me trying to solve this nonlinear system of equations, right? And generally, you get, if x is 0, both equations are true. So y can be anything. So you do get any point on the y-axis, but you also have, this also has to be true, right? So that's why you don't get any point on the y-axis. Y can't be equal to 700, for example, right? Because that equation, x squared plus 2y squared less than or equal to 6, also has to be true. So it really, if you wanted to, you could actually stick this equation in here to remind you of that fact. Right? But usually we kind of we're not worried about it. We would just find the critical points and then we would throw away any critical points that aren't in our set, right? That's usually how we would do that. But x equals 0 satisfies both equations. So there's no restriction on y. And in fact, if you were to graph x squared plus y. So here, maybe let me see if I can't graph this. So x squared y. And then let's share that. Okay. So what you can actually see, oops, that's not what I want to do. So what you can actually see now, I can't restrict this to just the ellipse, right? It kind of has to plot it on a rectangle. But what you can see is, remember, the critical points are sort of like where the tangent plane is equal to 0, where it sort of flattens out. And you can see, yeah, along the entire y-axis here, right? It's flat, right? Not along the x-axis, right? If we kind of look at the x-axis, it's not flat, right? It's sort of slopey here, right? But if we look along the y-axis, it's flat, right? It's like if you took a piece of paper and you tried to make the piece of paper lie tangent to the curve, that piece of paper would lie flat if you kind of, well, maybe not paper, maybe cardboard or something, right? Something with some rigidity. And if you balanced it on here, it would just be flat. But if you sort of leaned it against here, it would kind of go up and down. So this is why, if you look at this function, you can see that the y-axis are all just critical points, right? And so that's why we do end up getting that. And that's not, that sort of thing generally can't happen in one variable. I mean, it could, right? We could artificially make it happen where the derivative was constant for a long period of time. But it is something that happens much more often in multivariate stuff, right? And you can get these entire submanifolds that are critical points. It's just like the roots of a function right, of roots of functions in R typically are single points, right? You don't get like, usually you don't get entire spans where they're equal to 0, but yeah, that can totally happen in Rn. Okay, anyone else? Any other questions? Because we're running out of time here. Just about done. I guess there's not that many people left anyway. No problem. See you, Christian. All right, everyone. I'm going to call it a day then. Nobody else seems to have any other problems. Yeah, no problem. Thanks, everyone. Have a good Wednesday. I'll see you Thursday night. No problem.